Right, our next talk is from Lilley, who works at Xero. He will be talking to us about bug hunting with static analysis tools. Over to you, Moss.
Sweet. Thanks everyone for being here. This is my first talk, so if I seem a little nervous, it's because I am. So yeah, I'm going to talk to you a little bit about bug hunting with SAST and start off with a bit of a thanks to our sponsors for making this happen and making sure that we could all be here and have this great conference over the next 2 days. It's just a bit of who am I. Like it was mentioned, I work at Xero. I've been there for about 2 years now. It's been kind of my first job out of uni. I've been doing my best to kind of leech everyone's brains around there because there's some great people I get to work with every day, and it's just been great to learn about security and all the cool stuff and the different areas we have and can learn about and work on around that. So just a bit of context for this talk as well. This is stuff that it's mainly around scanning C# code, just because that's the code I get to work on at work. And so I get away with doing a bit of prepping these slides and working on this on a bit of company time. And so some tools out there for SAST I kind of looked over and didn't really use too much just because they don't have great C# support. And some of my coworkers mentioned I might sound like a bit of a shill just because I get a bit enthusiastic about these tools. Rest assured, I am not getting paid to say any of this. And any enthusiasm is just because I found something that worked and I just got a little excited. So a bit of an overview. We're going to run through 2 different bug types, XXC and Ssrf. I know there's a talk about XXC later today, so I'm not going to try steal too much thunder there. So we're going to talk about both of these bug types. We're going to talk about what they are, how they occur, what it looks like when a developer might write some code that's vulnerable to one of these bug types. And then we're going to start looking at some SAST tools and how we can use those to detect and hopefully provide a developer with a bit of info on how to fix these problems as they arise. And I guess another caveat is that the tools I was looking at, I was very much focused towards being able to customize and write my own rules or queries so that I could fix the problems that were very specific to our use cases as an organization. And I was just like, this bug looks cool, I want to be able to find it. Cool. So a bit of an overview on SAST. If you don't know what that is, it's static application security testing. Think of it as white box testing. You have access to the source code. You can look through it. It's basically, you can do whatever you want with the source code up to running it. And once you start running the code, it turns into DAST, dynamic application security testing, which is the black box approach. You're looking at the input and output. A user's really, a tester or an application a DAST application is sending input to an application, looking at the output, trying to replicate a malicious user to see if we can get any interesting output and maybe some interesting bugs. So, XXE. Not sure why they didn't call it XEE. I don't know, double X maybe is a bit more interesting, but it basically stands for XML external entity. Sounds a bit odd. XML, for those of you that don't know, is a data storage method. It's still used in lots of applications today, and it's actually the XXC is number 4 on the OWASP top 10, so it's still pretty relevant, and any applications running C# still use it a lot. It's used a lot in Microsoft Office and a lot of Microsoft's tools. So here is a little bit of XML. It's not a nice bit of XML. It's a little bit of a malicious piece of XML. Have a quick think about what this XML document is trying to do. Cool. So this XML document has a DTD, or a document type definition. It's clearly underlined there where the DTD starts. And within this DTD, we're trying to include an external entity, something that's external to this XML document, in which case it's the password file on a computer. it can be kind of bad. Usually, we'll start with a password file just because it's usually globally able to be read globally, and then you can start looking for other interesting files that might lie on a computer or a server. And from here, we are now going to pass it into an XML reader that our developer has written. Have a think about what might happen when that evil XML file is read by this reader, and we're running it on the latest version of .NET Core. Sweet, so Microsoft is really great at giving us some secure defaults. So they give us a great, nice little error that processing a DTD is prohibited in the document. Cool, good, job done, XXC solved, let's go home. Developers love to change settings, and no default is going to apply to everyone. So often, a developer might add some of their own settings without quite realizing some of the consequences involved. So if we run our XML reader now with some extra settings that our developers clearly nicely commented about what they're doing and what's going on there, we get a few more problems. That last evil XML file will actually read the password file on a server. And to get an idea of what's actually going on here, there's a line, adding a URL resolver means that file URL in our evil XML document is actually resolved, and that password file is read. Setting max characters from entities to 0 doesn't actually mean we read 0 characters. You actually read infinite characters. Who would have known? And so that's where your denial of service attacks come in, and actually just setting that DTD processing to pass is what enables all this, because by default it's set to prohibit, and we get that nice error we saw before. This next slide might look a little familiar from our first presentation, just to kind of go over and emphasize that DOS vulnerability. It's a billions of laughs attack. It's a billion laughs, believe it or not. First line has about 10 laughs, and each line goes exponentially more until you get to the bottom and you've got 10 to the power 9, which is a billion, and as it was mentioned, quickly eats up any resources on a computer or a server, and bad things happen. Cool. So how can we fix this? How can we solve this? How can we help developers to not do this? This is a nice little bit of regex. If you're like me, you don't actually know how to read regex, and you have to Google it every time. And there's a great website, Regex 101, I always default to, but you got to start somewhere. And what this regex is doing in English is checking to see if the resolver is not set to null. And this is handy because our resolver it's one of the few things we can look for amongst those three I kind of mentioned earlier. And it's null by default on all the newer versions of .NET. I think since 4.5 it's been set to null, which is great. And so when we start using this regex, and we can leverage some tools like DevSkim is one we've been looking into and using. It's made by Microsoft. It's an IDE extension which supports most of your popular IDEs. Open source, it's great. We can start doing stuff like this, where a developer is writing their code, they're getting some nice squiggly lines to say, hey, something's going wrong, something's awry, and they can actually fix the problems as they occur. So as we can see, you get a bit of details, bit of information for your developer as well. And then this last part here is actually changing that DTD processing.pass to prohibit. And that's really cool, to be able to shift left as I think everyone's trying to do at the moment, and to be able to provide this feedback and help to developers in the IDE is really cool, and it's a really great thing to be able to do. Cool, and so now we're going to have a look at Ssrf, server-side request forgery. So if you don't know what that is, it's kind of like we've gotten a totally legit person who wants to talk to a website, and then maybe there's another website that's internal to a network that they can't access. So in this case, we've got snakeoil.security, and snakeoil.security has a great scanning tool you can use to scan websites, and maybe they provide a little report. I don't know. Someone told me that you have to own all the domains that you show in a presentation. I don't have $3,000 spare to buy snakeoil.security, so yeah, good luck. Okay, we've got snakeoil.security, it's scanning something like Google, and maybe we tell it, hey, I want you to scan an internal IP address, and suddenly it's returning a report on that, and you're like, this is something interesting, this is a little different. This is basically when Ssrf starts to occur. So we've now got our Snakeoil server talking to an internal server that we couldn't access from the internet. And so in the context of the cloud, this gets a bit more interesting, because that internal server is a metadata endpoint, and if anyone's familiar with AWS, those metadata endpoints can give you some nice credentials. And if you're also familiar with AWS, you'll know that identity access management is hard. It's really easy to just give something access to all the resources in your account, and it works, and you're done. But in this case, if our snakeoil.security server had access to a lot of resources and identity access management was done bad, then our malicious user suddenly has a lot more surface area and a lot more they can work with because they have access to this whole AWS environment. Cool. So how might a user start sending, how might a developer send these external requests? This is where we're starting to look at how can we fix it, how can we detect it, how can we help the developer. So one of the many ways in .NET C# is to use this get async on an HTTP client into a URL. So then we come into this question of, okay, well, I could use the regex I did before, just find get async if there's, and I don't know, make sure that it's not coming from a malicious user. This is kind of where we start running into problems of false positives, and if we're throwing red flags every time a developer's trying to use a get async function, they're going to pretty quickly stop using whatever we provide them to, that puts up those red flags. So this is kind of that question of, okay, where is the URL coming from? Is it coming from a developer setting? Is it coming from something that a user's, or some user input? So for this, I found a nice tool made by, it's currently owned by GitHub called CodeQL. And CodeQL introduces this idea of tank tracking variables, checking to see, okay, has this come from a user? And as a variable flows through the code, you know, it'll change a bit, but it still has that user input at one point. And so we start looking at this idea of sources and sinks. So our sources are the user input, and our sinks being, okay, a function that that's eventually fed into. So we've got our remote sources and our get async function. And from here, I'm going to be displaying a lot of code. I apologize. Hopefully it looks all right on the screen. Sweet. So in CodeQL, we define a sink. So this is where our code is ending up. We start by kind of saying all the possible HTTP functions. There's a lot more. I didn't want to include them all on the slide. And we're basically saying that we want to find any HTTP call with an argument that's any of these get async, get string async functions. And then by default, CodeQL does a good job of knowing most of the remote places we can get data from. So we don't have to worry too much about customizing and defining our own remote source. So this is kind of what it looks like in the end. You write a bit of config, you specify, okay, I want a remote source and I want the sink to be my HTTP call, and we can start running it on projects. Bit of a caveat, CodeQL, the license for it, you can know, it's only free to run on open source projects, so don't go playing around with it on any closed source projects or you might get into trouble. And so whenever you want to POC something out, you know, I went onto GitHub, found a nice open source project and ran it against this to see what I could find. It was a little bit interesting. So this is a bit of an example of what the output looks like. we can see that from some kind of form that it's passing through a few different functions and it goes to an output URL, which we'll see in a moment. So this is what the code looks like, the underlying code. So it's actually a captcha. And so whatever that request form is coming from the user, it's then being passed into this validate function. And inside the validate function, it's passed into a URL variable where it's formatted, and then that's where we see it's sending that outwards HTTP request. Pretty cool. Maybe not quite Ssrf, but it's a start, and it's cool to be able to just run this against something and then have that output and be able to at least work through it. It's a little bit of refining to do, and yeah, I think that was, so next slide. Cool. Sweet. So just a bit of a recap. There are different, not all vulnerabilities you're going to be able to find the same way. For our XXC example, we were looking more at misconfigurations and how something was set up or programmed, and that was what was causing the vulnerability. And so we were able to detect that reasonably easily through regex to be able to say, hey, maybe don't use this setting, maybe have a talk to someone else, let's have a bit of a discussion about why we need this setting and not something else. But when it came to something like Ssrf, we can't just use that same method of regex. We need to look into some other tools which maybe can't run in the IDE but can run as developers are putting in pull requests. And a little bit further down the development cycle, but still pretty far left. And yeah, so another thing I thought was pretty cool is that CodeQL, or the GitHub Security Lab, has a bug bounty program around writing CodeQL queries. So if you write a query and you find a cool bug on an open source project, they'll pay you for it. And yeah, it's a bit different to your usual bug bounty, but I thought that was pretty cool to be able to contribute and help open source in a way, and to kind of learn some things as well. I think that's all I really had to say. Just like to thank you all for coming. I hope you learned a thing or two, got a bit curious about some SAS tooling and maybe writing your own queries and having a look at some different things today. Yeah, cheers. Thanks for coming.
Awesome. Thank you very much, Moss. Does anyone have any questions for Moss? Because we've got a few minutes until the next talk. Any questions? We actually have an online question, so let's hear what that is. The question is, can .NET Roslyn analyzers do something similar to CodeQL to identify sources and sinks? Wow. Do you have an answer for that?
I think I know who it is. Anyway. Yeah, so the question was about .NET Roslyn analyzers, and while for those of you who don't know what Roslyn is, it's the .NET compiler platform, and you can do similar things. I haven't looked at it specifically for sources and sinks, but I know there's people on my team at work who've been looking at similar things for just leveraging that platform for other things. I think I didn't end up looking at Roslyn analyzers too much just because I wanted something that could be applied and applied to other programming languages and a bit more diversity on the tools. Yeah, not quite the answer, but I feel like it can. I'm not 100% sure because I haven't really looked into it.
Awesome. Thank you very much.